I will tell you about asymptotical behavior of probabilities of first-order properties of Erdos-Renyi random graph. And let me start from some definitions. First of all, I will remind the definition of first-order properties. So the first-order properties are expressed by first-order formula, which are built of relational symbols, logical connectivities, variables, and quantifiers. So just for example, let me consider some properties. So property of a graph to be complete is the first-order property. It is because it is expressed in the formula from this language. And the property of a graph to contain a triangle also the first-order property. But for example, a property of a graph to have chromatic number k is not the first-order property because it isn't expressed in terms of the first-order language. And we consider a random graph G of NP, which has n vertices, and all edges appear independently with probability p. Let me consider arbitrary graph G and the property of containing this graph. And it is easy to see that it is a first-order property. And it was proved in it was proved by Bela-Bolobash that for this property there exists the threshold probability. It is denoted by P0. It means that for any P asymptotically larger than P0, probability of containing graph G tends to 1, and for any P asymptotically smaller than P0, this probability tends to 0. But if P is equal to P0, then there is a limit probability, and it is not equal to 0 or to 1. Here you see this notation, maximal density of graph G. So it is the maximal over the densities of all subgraphs of G. And if this density equal to the density of the graph G, then the graph is called balanced. And if all densities of all subgraphs are smaller than this value, then this graph is called strictly balanced. So it is easy to see that if we consider any irrational alpha and P is n to the minus alpha, so let us also consider this set of properties, all properties of containing graphs and all negations of these properties. So for any property from this set, either its probability tends to 0 or to 1, because this threshold equals to n in the rational power. So if we have the probability, if we have such probability, then either probability tends to 0 or to 1. Well, this property is written here. And it turns out, and it was proved in 1988 by Spencer and Shelah, that this result can be extended for all first-order properties. And it is called 0-1 law. So the random graph obeys 0-1 law if for any first-order property, either its probability tends to 1 or it tends to 0. So let us denote by P a set of functions, a set of all functions P small, such that G of NP obeys 0-1 law. And in 1988, Spencer and Shelah proved that if alpha is irrational, then 0-1 law holds. But if alpha is rational from this interval, then 0-1 law doesn't hold. the question is, can we consider some subset of all first-order properties such that the 0-1 law holds for some rational alpha 2? And the answer is the following. We can consider the properties which are expressed by formula with bounded quantifier depths. Well, let me remind the definition of quantifier depths. If we consider such formula with no quantifiers, then its quantifier depth equal 0. If we have a formula with quantifier depth k, then quantifier depth of negation of phi equals k as well. And if we consider two formula with quantifier depths k1 and k2, then quantifier depths of this formula equal maximum over k1 and k2. And if we add the quantifier, then the quantifier depth of new formula equals k plus 1. Okay. And so we consider the class of first-order properties which are expressed by formula with quantifier depths bounded by the number k. And we denote this class by Lk. And we say that the random graph obeys 0-1 k law if for any property from this set either its probability tends to 0 or to 1. Let us also denote by Pk the class of all functions p such that the 0-1 law for this class holds. In this case, we say that the random graph obeys 0-1 k law. But there are some cases when we have a property and there are different formula that express this property, and this formula have different quantifier depths. In this case, the property is in the class Lk if its minimal quantifier depth is at most k. So in this case, quantifier depth equals 2. In 2010, we proved that if alpha is less than 1 over k minus 2, then 0-1 k law holds. And after that, we consider alpha which are close to 1 and prove the following result. So let alpha be greater than 1 minus 1 over 2 to the k minus 1. So it equals to 1 minus 1 over 2 to the k minus 1 plus beta, where beta is some positive rational number. And there are some beta such that there is no law, and there are some beta such that 0-1 law holds. So if beta is not in the set Q, where Q is the set of all rational numbers a over b such that a is at least 2 to the k minus 1, then 0-1 k law holds. So for the illustration, I give such intervals here. So the first interval is this, and in all alpha from this interval, alpha from this interval, 0-1 k law holds, and then such interval, and so on. And the last interval is from the previous theorem. And here we have a large interval from 1 minus 1 to the k minus 1 to 1 over k minus 2, and we don't know anything about this interval. And so what about the points that are boundary points of the endpoints of the interval? First of all, we prove that if alpha equals 1 over k minus 2, then 0-1 law doesn't hold. And we also prove this result for some beta from the set Q, but we have only a finite number of these, let me say, critical points. So if there is no law, I will say that the point alpha is critical. In this set Q, there are infinite number of points, but we prove the negation of 0, 1 law only for finite number, and we don't know anything about another number. So once again, let us consider all critical points in the interval from 0 to 1, but let me consider not alpha, but 1 minus alpha. So if alpha goes from 1 to 0, then 1 minus alpha goes from 0 to 1. The first critical point is 0, and alpha equals 1. Then there are 2 points, 1 over 2 to the k and 1 over 2 to the k minus 1. I didn't say are they critical or not. And then the point 1 over 2 to the k minus 2 is a critical point. Then some critical points. And then there are some points that we know that are critical and some points that we don't know. And after that, this large interval. And the last critical point is 1 minus 1 over k minus 2. Recently, we proved new results, and also we proved that these black 2 points are not critical. So we know 2 to the k minus 2 minus 1 first critical points. Once again, we have this blue interval, and we know everything about it, and everything about this interval. Is in this interval we know some critical points, and we know nothing about this interval. Okay. And now I will tell about the proofs of 0, 1 laws. All these proofs are based on the Ehrenfeld theorem. So first of all, let me remind the definition of the Ehrenfeld game. Let me have 2 graphs, G and H, and K rounds, and two players, spoiler and duplicator. In each round, either spoiler or duplicator, in each round, the first move is the move of spoiler, and the second move is the move of duplicator. And spoiler can choose any graph that he wants and any vertex in this graph. So for example, in the first round, spoiler chooses the first graph and this red vertex. And then in this round, duplicator must choose another graph. And any vertex that he wants, for example, this blue vertex. And then the next round, spoiler again can choose any graph and any vertex from this graph. For example, now he chooses another one. And then duplicator chooses this graph and this vertex, and so on. And so if k equals 4, then we have 4 rounds. And after that, spoiler wins if and only if the induced subgraphs are isomorphic. So we see that these subgraphs are isomorphic, and then duplicator wins. And we say that duplicator has a winning strategy if he wins always. So he has a winning strategy independently of the strategy of spoiler. And now Ehrenfeld theorem, the theorem about the connection between first order properties and Ehrenfeld game. In 1960s, he proved that the following result, let G and H be 2 graphs, and then for any first order property L expressed by formula with quantifier depth bounded by K, this property holds if and only if duplicator has a winning strategy in the game of Ehrenfeld for graphs G and H with k rounds. So if we have some property and we know that its quantifier depth equals k, and we know that the first graph, for the first graph this property holds, for graph G for example, and for the second graph H this property doesn't hold, then the spoiler has a winning strategy in the game on these graphs with k rounds. For example, let us consider the property of containing a triangle, and this graph doesn't contain a triangle, and the another graph contains, and then there is a winning strategy of spoiler in the game on 3 rounds, and we see that spoiler can choose a triangle, but duplicator cannot do it, and so spoiler wins. And there is a corollary from this theorem, and we use this corollary to prove 0-1 laws. Well, 0-1 law holds if and only if for any natural k, almost surely duplicator has a winning strategy in a Ehrenford game on k rounds. And if we want to prove 0-1 k law, then we should prove that duplicator has a winning strategy almost surely for any k. And now let us use this corollary to prove that 0-1 law doesn't hold if k equals 4 and a equals 13 over 14. So from the previous slide, let me find it. From the previous slide, we see that this is this case. If k equals 4 and beta equals 2 to the k minus 1 minus 2, then alpha equals 13 over 14. So 0-1 law doesn't hold. Well, to disprove 0-1 law, we consider this graph. Well, it looks like fish, and it has 13 vertices and 14 edges, and its density equals 14 over 13. And this graph is strictly balanced. Once again, it means that its density is maximal, and all its subgraphs have smaller density. And from the result of Bolbash, it follows that our random graph contains this fish graph with positive asymptotical probability. And we also know that with positive asymptotical probability, it doesn't contain a copy of any graph with at most 13 vertices and maximal density at least 14 over 13. So if it has, if it doesn't have a subgraph with small number of vertices but large density. And we want to disprove 0-1 k law, in this case 0-1 4 law. It means that we want to find the strategy of spoiler which is winning with a positive asymptotical probability. So let us consider two graphs, G and H, and the game on these graphs on 4 rounds. And let G contains our graph, and H doesn't contain a copy of any graph with at most 13 vertices and maximal density at least 14 over 13. So G follows this first property and H follows this second property. So if we prove that spoiler has a winning strategy in this game, then of course in the game on 2 random graphs, spoiler has a winning strategy with positive asymptotical probability. So let us discuss this strategy of spoiler. On the top of the slide, you see the graph G, and here you see the graph H. And So in the first round, spoiler chooses the graph G and the vertex x1 from this graph. And then duplicator chooses any vertex y1. And there are two cases that we consider. In the first case, there is a cycle which contains y1, and the number of the edges in this cycle is at most 7. And the second case, when the graph H doesn't contain such a cycle. So in the first case, let spoiler chooses this vertex x2, and let duplicator chooses this blue vertex y2, which is not in this cycle, which is outside the cycle. Then there should exist a triangle which contains the vertex y2, because if there is no such a triangle, then spoiler can choose these two vertices and wins. So there should be a triangle, and this is the shortest path between the vertices y1 and y2. So let in the third round spoiler chooses this vertex, and duplicator chooses any vertex y3. It is easy to see that there should exist a path between the vertex y2 and y3 with two edges, and the same path between the vertices y1 and y3. Because if, for example, there is no vertex which is adjacent to y3 and y1, then spoiler chooses this vertex and wins. But if there is a vertex which is adjacent to y2 and y3, and a vertex which is adjacent to y3 and y1, then this graph has density 13/14 and only 13 vertices. And we know that graph H doesn't contain such a subgraph, so a duplicator cannot choose such vertex y3, and spoiler wins. So let in the second round, duplicator chooses a vertex from the cycle. Then once again, the vertex y2 should be in some triangle. If this triangle doesn't coincide with our cycle, then the density of this subgraph is too large, and the graph H doesn't contain such a subgraph. So our triangle should coincide with our cycle. Yes. So our cycle is a triangle, and in this case, the vertices y1 and y2 are adjacent. But the vertices x1 and x2 are not adjacent, and so spoiler wins again. And the last case, when there is no small cycle which contains the vertex y1, so let there be a triangle which is close to the vertex y1. I mean that the number of edges between this vertex and this vertex is at least 4. Well, in this case, spoiler chooses this vertex, and we see that there is a path of length with 4 edges which connects the vertices x1 and x2, and the another one with 3 edges. And there should be the same situation in the graph H. Well, it is easy to see that in this case, the picture should be the following. And duplicator should choose this vertex. Only in this case, he has a winning strategy. But then, spoiler chooses this vertex, and duplicator should choose this vertex. But in this case, these two vertices are adjacent. But the vertices x2 and x3 are not adjacent, and so spoiler wins in this case too. Okay. And on the last slide, I want to tell you about some open questions. which I'm interested in. So first of all, we don't know what happens when alpha is greater than 1 over k minus 2 and isn't greater than 1 minus 1 over 2 to the k minus 1. So this situation is rather complicated because there are so it's a combination of sparse situation and density situation, and there are different kinds of subgraphs and small structures in our random graph. So it is very complicated to consider alpha from this interval. And in 1988, Spencer and Shelah in their work proved that there exists a first-order property, an infinite set S of rational numbers from 0-1 interval, such that for any alpha from this set, random graph G of n to the minus alpha follows the property which exists with probability which doesn't tend to 0 or to 1. From this result, obviously, it follows that there exists a natural number k such that the number of critical points for 0, 1 k law is infinite. And but we prove that for any positive epsilon, the number of critical points in this interval is finite. But we don't know if this number is finite or infinite in this interval. And the another question is, are there such finite subintervals in this interval? Well, that's all. Thank you very much.